in what topology, what structural features do they have, and so on. So before, this is sort of an ambitious question at first, before you get into that, you can ask a simpler question, which is the following. Assume you do have a global in-time solution, which conserves mass and energy, so very nice and smooth. What can you say as a consequence about the solution itself? So it's not very hard to show by basically using a virial theorem type argument. It is not very hard to show that the support of the solution, so if you imagine that this density is compactly supported, the support of the solution, so virial theorem plus global existence, this immediately implies that the support has to grow. And in fact, it grows at a linear rate if gamma is less or equal than 5/3. And then there's a bit of a transition. So 3 times gamma minus 1 if gamma is strictly bigger than 5/3. Okay, so what do I mean by virial theorem? Just take a time derivative of the integral of u squared against the Galilean boost, so x minus 2u, rho, and then perform some sort of integration by parts, and you will discover this state. If the solution exists, this has to happen. Now, why is this? Oh, by the way, so it's hard to attribute this to a single person because it's been sort of around in various guises in the physics literature. But there's an excellent paper by Sideris from 2014 where you can sort of learn everything about this and various consequences about this fact. Now, why is this consistent? Why is the expansion of the support consistent with global existence? Why does it have to do with one another? You can think of the mass conservation law, which sort of in so if omega of t is this changing support of the density rho, which sort of in very average, very rough sense tells you that if this is to remain constant, then the decay of rho has to do something with the expansion of omega of t. These two things have to work together. So question 1. So this is somehow first question you may want to ask, being aware of this fact. Can we find any, say, special solutions with this that exist globally? And a fortiori you have to satisfy this type of growth. So here I'm interested in a situation where my initial density is supported in some finite law. And now this thing sort of should conceivably expand. Now the answer to this question is yes. And this is due to another paper of Sideris that was released on the archive in 2015 but published appeared this year, where he constructs a finite parameter family of solutions that exist globally in time. And before I tell you what they are, let me draw the picture of their support. So this might resonate with some of the things we've seen in the previous talk. So the support of these solutions are ellipsoids. So this is an ellipsoid. And they're expanding in time. I'll give you formulas in a second, but this is what they look like. Okay. So the support of these, let me call this support omega of t. So the support of omega of t is given by an image under some invertible matrix A of t of the unit ball. So to specify the solution, I have to tell you what this matrix is and what the density and the velocity are. So let me tell you what the density and velocity are, and then I will finally explain what this matrix A has to satisfy. So the density of these special solutions is given by the determinant A of t to the power minus 1 times the following function, 1 minus A inverse of t x squared, positive part to the power 1 over gamma minus 1. Okay. UATX is simply A dot of t, A inverse of t x. So I claim, given an A, that I will give you in a second, these formulas have to hold in order to satisfy the Euler equation, and A itself solves the following ODE. So A double dot of t equals the determinant of A of t to the power 1 minus gamma, and then this is my notation for the inverse transpose. So here's the statement. Solve this ODE with suitable initial conditions. Plug those values into rho A and UA as given. That will solve the Euler system. Moreover, this nonlinear ODE has a global in time solution. This can be shown. This is, if you wish, this is the content of the theorem of Sideris. So if you want to count the parameters that sort of parameterize this family, this moduli space of solutions, they are essentially the dimension of the initial data for these the space of initial data for these matrices. Okay. Don't worry, I will re-examine this on 2 more occasions, and then everything will become clear how one arrives at these things and so on. So before I state our main theorem, I just want to say that all this. I could have or should have said it even after the statement about the variable theorem, suggests that the natural framework, or rather the framework in which you can only see trace out the trajectories of the particles and say something about the shape of the support, is that of a free boundary problem. So really, the problem I want to look at are these same equations, but set in a moving domain. And once you impose the presence of a free boundary, you have to say something about the boundary conditions. So the pressure, which in this case translates to, pressure has to be 0, which in this case simply translates to rho having to be 0 at the boundary. And then you have to say something about the movement of the boundary, which is of course very well understood, very well known to this audience. The normal velocity of the boundary is simply driven by the fluid. So this is at the boundary. Okay, so sorry, this is bad. So theorem. Again, this is a joint work with Hadzic. If gamma is between 1 and it's lesser or equal than 5/3, then Sideris ellipsoids, or as I shall call them from now on, affine motions. I believe in the previous talk we've seen examples of affine motions as well. At least this terminology is due to Maida, I believe, from early 80s. That's where I've seen it. Are nonlinearly stable. So these are time-dependent solutions, so it's a priori not clear what I mean by saying stable. What I mean by this, that in a suitable topology and in a suitably rescaled sense, there is a neighborhood, open neighborhood around these Sideris motions, such that the solutions launched by the initial data from that neighborhood exist globally in time and remain close to this manifold of this finite parameter space of affine motions. So that is the statement. Okay, so so this is loosely stated, it's an informal statement. As we go through the talk, it should become more apparent what I mean by this precisely. It turns out that practically the only way we can prove this is by reverting to Lagrangian coordinates. And this would happen later on. Now, before we get into any technicalities, I would like to go back to the Sideris motions and tell you how he derived it. And then tell you, and then re-examine it from a different point of view, which involves using language of sort of group symmetries and invariant group actions, which is not an exercise, which is not only an exercise in abstract algebra, but in fact informs a way of asking the question of nonlinear stability. So this is part 2 of the talk. So part 2, symmetries of the Euler flow. So first, how do you come up with these solutions? Let me tell you what Sideris did. If you're interested in understanding how the support of the particles evolves, a natural set of coordinates is that of Lagrangian coordinates, as it was already mentioned in the previous talk. So let's introduce Lagrangian flow map. Let's call it zeta for a moment. So zeta dot of Tx is the velocity field evaluated along the particle trajectory. And all that Sideris did, he made the following ansatz. So he assumed that the particle trajectory has the shape of some matrix acting on X. Okay. So this is a separation of variables argument. If you plug this back into the Euler equation, you will discover the ODE that it's right here. You will discover the ODE star. And these formulas will pop up out of a separation of variables argument. That's all it is. So this ansatz, at least in the literature that I've seen, is called an affine motion. And it's reasonable. For instance, the motion that you mentioned in the previous talk, in the one that squishes, it would belong to this class of solutions. Okay, so now I will give you perhaps a more complicated way of deriving these solutions, but as I said, it pays off because it will tell us how to set up the global stability problem. So I should say that in the Sideris paper, he also does this for incompressible flows. So that example in particular is there. And it just happens to solve both Euler and Navier-Stokes because of this linear ansatz.
So for incompressible, you have a condition on A, or?
Right, so it generates a certain condition on A. The divergence of U has to be 0, which will translate into the condition that well, A is not just invertible, but it's A dot A inverse has to have a vanishing trace, something like that. In other words, you can never generate expansion. If you expand in this way, you have to. So he constructs what he refers to as the full breakfast menu of shapes in the incompressible case. He gets the pancakes, so then you squish only one dimension, but you can squish both, so then you get the
American
breakfast. American breakfast, that's right. Okay, so symmetries. So now I propose to do something else. Let's fix an invertible matrix. let's consider the following change of variables. So I wish to transform a solution of the Euler system into a different one. And the way I'm going to do it, well, I'll give you some formula. I want to rescale space, time, and the unknowns in a certain way. So I define rho tilde implicitly by the following formula. So rho of p and x is the determinant of A inverse, rho tilde of s and y. S and y are my new time and space. And then u of t and x is the determinant of A to the following power, 1 minus 3 gamma over 6, A acting on u tilde of s and y. And it is not hard to guess what y has to be. It's simply A inverse x. And s satisfies this particular scaling, so s is given by the determinant of A to the power 1 minus 3 gamma over 6 times t. Okay, so this looks like a complete mess, but if you accept this, you can do the change of variables and you can ask, what is the system satisfied or solved by rho tilde and u tilde? So if you do that, you will discover that rho tilde satisfies the continuity equation again, and u tilde solves, well, okay, so if this were a gradient of rho tilde to the gamma, this would be the same system, but it is not. This gradient here gets altered by what I call lambda of A, and I believe in your talk this was the Cauchy-Green strain tensor. So lambda of A in the compressible context is the determinant of A to the power 2/3 A inverse transpose. So if this is 1, then it will be the exact same object. Okay, so this change of variables turns rho and u into solutions of a different system, which is almost the same system as before. In fact, it is an instructive exercise to ask. So remark 1, when is this an exact symmetry? Well, that would be the case if lambda of A is the identity matrix. And lambda of A is the identity matrix exactly then when A is the so-called conformal matrix. So this means that A divided by the determinant of A to the power 1/3 is a rotation. And this exactly captures the intuition that you can scale and you can rotate, and these are invariances of your system. And second remark, by the way, you may ask, how did I guess those exponents? Well, you make a general ansatz and then you do some algebra. And you discover something quite disturbing at first sight. Namely, there is an infinite family of invariant rescalings, or quasi-invariant in this sense. But only one of them keeps the mass conserved. Okay, and that's the guy we are interested in. So this is a mass-critical rescaling. Okay, in all honesty, this was a pedagogical exercise. This is not really what I want to do. If I have some type of symmetry or quasi-symmetry in this case, which is mass critical, a natural question to ask is, can I modulate on this parameter A? In other words, can I find a family of solutions where A depends on time, which will honor these symmetries? In other words, can I repeat the same analysis, but this time I want to allow the matrix A to depend on time. So this is a very natural thing to do, and in fact, now you have to change your scaling, but you do it in the obvious way. You introduce a new parameter where this now depends on time, this depends on time. And all these a's here now have to depend on time. And as you can imagine, the moment you allow for a time dependence in this matrix A, when you carry out the chain rule, the change of variables, and so on, you get a complete mess. Because now the time derivative will hit A, okay, and you have to make sense of it. So, actually, there is another seemingly structural miracle, but it turns out it's something that simply reflects the symmetries of the equation, and the parallel to it exists, for instance, in the context of other dispersive problems like nonlinear Schrödinger equation. So now I want to do the exact same thing. Now I want to do the exact same thing. I would like to derive equations satisfied by rho tilde and u tilde, allowing this dependence. But it turns out you do not want to use u tilde as your new velocity variable. You want to augment it by sort of an affine correction, which takes this as is my notation for a derivative with respect to s, a inverse y.
Could you try to make that not in shadow? Yeah.
Okay. Now, if you do that, and you do this calculation, you discover that ds of rho tilde plus the divergence of rho tilde and this new velocity u is 0 again. And the question is, what happened with the momentum equation? So here you finally start paying the price. So ds u plus u dot gradient u. This is the material derivative of u. It stays there. Now suddenly you pick up a new term. Exciting. Green is the color of hope, I think. So let's put it in here. The new term is some explicit algebraic expression. It's a matrix which depends on A and its derivative, acting on U. Then you pick up your, so I divide it by row here so that you get here some number. The same matrix lambda, the Cauchy-Green strain tensor, times the gradient acting on rho tilde to the power of n minus 1. And then finally, there's something shows up on the right hand side, and I'll put that in blue. Yet another explicit and maybe complicated looking expression that I will not write down, which depends on up to 2 derivatives of A times y. Okay, this is the structure of the new system. Okay, these things can be written down explicitly. I wouldn't worry about that. The point is, you can ask a very simple question. In this rescaled system, what are the steady states? So assume that u is just 0 and rho tilde is just a function of y. Then you immediately see that the first equation is satisfied automatically. In the second equation, any term that involves u vanishes. So to have a steady state, you need to equate the pressure term over there to the blue term. Okay. So this is, you do that, lambda, remember, depends on A, so you do that by saying that lambda of A, which is the strain tensor over there, equals this quantity here. And then with a minus sign, and then gradient of rho tilde to the gain minus 1 equals minus 1. Okay? You solve this. This is exactly the Sideris ODE expressed in the S variable. And this here gives you the profile that we have seen before, namely rho of y is 1 minus y squared, positive part to the power 1 over gamma minus 1. Okay, this profile, when you plug in y equals a minus 1 dx, this is exactly the Sideris, the affine motion that I discussed earlier. Now, the correct question at this stage is why go through all this to replace that beautiful separation of variables argument by this complicated argument here? Well, you see it immediately. If you take a steady state like this, then the question of saying what it even means for those motions to be stable is reformulated as a small data problem for this new equation, right? Because u equals 0 is precisely it corresponds to the expanding motion. So in a way, this is a correct rescaling that allows you to bring out to formulate the stability question. Okay, so this equation here, what we call it sharp. This is if you wish, a starting point for our analysis. So for the remainder of the talk, which is the next 20 minutes, I will speak about more technical things. All of which are absolutely necessary, at least from our point of view. But one thing that we can address right now is the following. Why should we even hope to see something stable in these variables? Well, it all hinges on the properties of this green matrix here. If this were, for instance, some nice positive definite matrix, this would give us an immediate damping effect in the Euler flow, which should hopefully stabilize the flow. So the hope is, because this blob is expanding, this blob of gas is expanding, the particle trajectories are moving away from each other. So they don't want to focus. So you're betting on precluding any type of shock formation or anything like that by basically having them move away from each other faster. So that's sort of the moral of this story. But you see, from rigorous point of view, to address this question, you have to deal with something which is absolutely there, and it's not going to leave you. These profiles, these density profiles, they're all none of them is differentiable, so they're all continuous, and then they have the first derivative is not continuous anymore, exactly at y equal 1. So whatever theory you want to use to prove well-posedness, you need to take into account, it needs to address this issue. It needs to allow for the support to keep this type of discontinuity at the level of the first derivative. So this is a problem. So let's make a few comments about that. So this is part 3, which has to do with sort of ideas of the proof, let's say. So this type of discontinuity that I just referred to, namely the fact that the normal derivative of rho tilde to the power of gamma minus 1. So the normal, let me actually introduce a notation. Let's call that profile WY. Okay, I just want to call it WY. And then let me call that exponent 1 over gamma minus 1. Let me call it alpha. This way, the density profile in these rescale variables is W to the power alpha. Okay. This type of discontinuity, namely the one which has the property of the normal derivative of W at the boundary, so initially it is strictly less than 0. This has been called, at least in some of the literature coming from hyperbolic conservation laws, a physical vacuum condition. So I did not come up with it, physical vacuum. And I believe it should be attributed to Taiping Liu, who popularized this notion and popularized the problem and the question of proving well-posedness, assuming this type of discontinuity. So W is an enthalpy. So what is W here? It's the initial density to the power gamma minus 1. The answer to the question of local in time well-posedness was provided surprisingly late. So only in 2010, in this free boundary context, this was solved using Lagrangian coordinates. It's independently by two groups of authors. One of them, Couton and Stoller, and the other one, Jen and Smooth. So they share certain similarities, and of course have some differences, but one of the common feature that both agree is absolutely unavoidable is using Lagrangian coordinates to address this question of even local and time positives. And for us, this is also a starting point, but instead of passing to the material Lagrangian coordinates in the original velocity variable, we will do this for this appended or modified velocity capital U. So that's sort of the first thing to do. So in other words, so we also use the Lagrangian coordinates, but they are adapted to capital U. So I'm noting my flow map by eta. Okay, so to explain the main difficulties, what I'm going to do, I will jump a few steps and write down what the equation is when you pass to eta as your unknown, and it will be fairly unappealing, let me put it that way. And then I'll break it apart term by term and tell you what flavor they have and what they actually do. So if you impose this change of variables, assume that A is one of these affine motions. So S goes to A of S is an affine motion, which in our language, so affine motion discovered by Sideris, which in our language means that quantity F2 of A is just matrix lambda of A. Equations take the following form. So dSS eta plus this green quantity ds eta plus lambda of A is given, eta. Then you have to take care of the pressure term, and this is potentially the most problematic term in this whole business. So let me write it down slowly, and we'll comment on it later on. So lambda gradient, because you're pulling back onto the initial domain using Lagrangian flow map, you have to pull back this quantity here. So instead of putting a star or something like that, I'll put a little eta. So this is my notation for the pullback. So this is some expression which involves also derivatives of the gradient of eta. And the pressure term, that rho tilde to the gamma minus 1, will become something of the following type. This weight W, which I've introduced over there, to the power 1 plus alpha. And then the determinant d eta to the power minus gamma. And just to reflect the presence of the density rho tilde here, there is also weight W. Okay, and this nasty thing equals 0. So these are the equations. First things first. You don't have to think too much about the details, but let's at least try to discover what type of equation this is. So here we see two time derivatives, two scale time derivatives. And how many spatial derivatives do we have here? Well, there is one hitting eta, and then there is one more coming from the pullback of the gradient. So there are two spatial derivatives here. So an optimist will say that this is like a wave equation. In other words, disregard the presence of the weight W here and all these other things. In other words, it would be quite convenient if this behaved essentially like a Laplace. And so this is the wrong answer. It is not a good. You do not gain good intuition by thinking of this as a minus Laplace. You have to account for a correction, which you can think of at the top order. So after you neglect all the little things that are of lower order, as a curl acting on a curl. So this is the right model operator here. In other words, if this were irrotational, this bit would not be here, and you would see a effective wave equation popping out, acting on the Lagrangian three vector eta. So this is first remark. So any attempt, remark one, any attempt to address the question of local well-posedness has to account for the presence of the curl and has to manage an estimate of the curl of your velocity field or your particle trajectories in a way which is independent of the energy estimate. Otherwise, you cannot close the estimates. So to summarize, curl, one big issue. Now let's talk about the green bit. So one thing that I stated in my theorem, I had a restriction on gamma, which said that the exponent gamma had to be less or equal than 5/3. That is essentially encoded in the structure of this quantity. When gamma equals, so this quantity effectively, modulo some technicalities, you can think of it as constant times 5 minus 3 gamma times the identity matrix. This comes out from the fact that you know everything there is to know about A, about the affine motions A. They solve some ODE, so you can extract properties of that object, and you discover that to the leading order, this is the structure of that term, which tells you that when gamma is less than 5/3, you have an effective damping effect in this problem. Okay, so this is where that restriction, that imposition of gamma less or equal to 5/3 comes from. Oh, that clock is wrong. How am I? Oh, I see. Okay. I have 5 more minutes. Good. Well, I'll speed up. I kept thinking I had 20 more minutes. So now you see that this is related to this restriction gamma less or equal than, let's say, less at this stage, less than 5/3. This puts in a certain damping effect in these variables, which you can think of as a stabilization mechanism. So it is precisely here where that intuition about particle trajectories spreading apart it sort of prevents focusing. It is precisely here where you see it. Okay, and then there's finally the third issue, which was recognized, of course, in the earlier, even in the local well-posedness context, and I've neglected it completely up to this point. I didn't tell you what is the effect of the degeneration of these weights. They are compactly supported, and they vanish at some point. So if you want to do energy estimates, the things we like to do, multiply by U, integrate by parts, you will see that your effective, let's say L2 type control over the gradient or whatever quantity you name it, comes with a weight. And that weight vanishes outside the bowl, and effectively degenerates the control that you have in the problem. So this is an absolutely fundamental issue that was already recognized. So the weights imply some sort of degeneration. So maybe another way to say this is if you if you were to sort of stay in the Eulerian variables and then symmetrize the system and then try to prove a local existence result, you would lose coercivity in your natural energy that is associated with the symmetrized system. It just wouldn't be there. So you have to take this into account. Okay. So let me now give a very brief sketch of how to address this, and this is already clear. And then if time remains, I can also tell you in how many ways I cheated today. And right, so what about the curl? Well, as I mentioned, if you want, you cannot hope to control the curl by running some type of energy-like estimate for the above equation. Even if you think of it as just think of it as a wave equation, forget about the weights and so on. So curl satisfies a transport equation on its own, and this is of course the reason why you can hope to close the estimates. In other words, let's go back to the Eulerian formulation. Let's forget about rescaling and everything. Let's just think Euler. Euler equation says that the material derivative of u plus a gradient of something equals 0. Okay? So gradients are annihilated by curls. So curl of this quantity is 0. Curl of the material derivative of u is going to be 0. When you pull back to the Lagrangian variables, this will tell you that the pullback of the curl operator, which you remember denoted by the index eta, of the velocities of the Lagrangian velocity v, of the time derivative of the Lagrangian velocity v, is 0. Or if you wish, dT eta is 0. When you pull back the t outside of this, you will discover that curl satisfies the transport equation. So this is E the Lagrangian variable. This is sort of you have to. They don't quite commute, so you have to t derivative will fall on eta. But if you work it out, that's what you see. So here this will not happen because remember our gradient is offset by the presence of this matrix lambda. So another way to put this, and this again relates to some terminology that we've seen in the previous talk. This lambda in itself generates a certain natural metric, which is associated with this problem. So the correct quantity to anti-symmetrize, so the curl, I guess we call it an augmented curl lambda, is going to be the acting on eta is going to be lambda gradient cross product eta. Okay? And it turns out that this quantity will satisfy a favorable transport equation. So this is this at the top order effectively decouples from the pressure term, and this is the reason why you can produce estimates of the curl component of the vector field eta independently of the energy estimates. It's a cartoon, of course. You have to do some work. So this is a critical quantity, and if one were so inclined, one could use more geometric language to re-express this as a natural curl associated with a certain metric, but maybe this is at this level not so important. Okay, so curl lambda eta, good transport property. And finally, I have to tell you, even if all this is true, how do you address the problem of the weights? Perhaps the easiest cartoonish way of seeing what the problem is, just write down the following wave equation. So UTT minus the divergence of some weight of gradient u, say equals 0. I believe some members of the audience would rather have a minus here and a plus here, but and if you do that, multiply by u, integrate by parts, dtu and integrate by parts, you discover that the natural energy, well, it's the integral plus the integral of W gradient U squared. So this is the natural energy that you control. So, so what is so clearly you don't control the full gradient in the region where W is very small. So how do you effectively say what is the actual unweighted Sobolev norm that you can control by this? Well, you use the Hardy inequality. To do that, you have to know exactly what W looks like, but the physical vacuum condition kicks in precisely at this stage. A restatement of the physical vacuum condition due to typing U is that W behaves like the distance function to the boundary. Okay, now you're really in the regime of the Hardy inequality, and in this particular case, if you had only one power of W here, this would tell you that effective norm that you can control by this is U in H1 half. So this is the exact scaling. So in this problem, 2 time derivatives go like 1 space derivative. That is the effective scaling of this equation, which is kind of quite unusual. Of course, if you have higher powers of W, this offsets the scaling, but you sort of know what to do. And the final resolution, this is the final thing I will write down. What are the function spaces where you actually close estimates? Well, you're working on a domain which is fixed to be a 3-dimensional unit ball. The directions that are tangential to the boundary, they do not affect the weighted W because it only depends on the radial component. So this weighing business does not really enter at that level. However, each time you apply a normal derivative, that is the y derivative or the r derivative, something new has to happen. So the correct scaling for this problem, so if you apply, let me use this notation for tangential derivatives. If you apply, say, and beta is a multi-index, if you apply this many tangential derivatives to your unknown eta, and you apply a normal derivatives to your unknown eta, then the weight you have to put in is going to be W. So here I need a gradient. W to the power 1 plus alpha. This is dictated by the equation. This is not surprising. What is interesting is the addition of this power A. So each time you apply one normal derivative, you have to add a power of W in your equation to accommodate for the loss of control that I just explained. Okay, and then for the, oh, I didn't tell you, this has to be squared, and then integrated over y, and then you do the same thing, but for the time derivatives, because of the weight, where is it? Because of the weight alpha, rather than 1 plus alpha, you get this. And because I'm not interested in any optimal regularity, you take a lot of these derivatives. So the idea is you sum, so your energy is summing this expression over all pairs of indices satisfying A plus size of this index beta less or equal than some capital N. This capital N has to be taken large enough, if you wish. And this is your energy. It depends on the number of derivatives. This is your natural energy in this problem. It is with respect to this energy that you can finally make use of the damping effect that I mentioned and close the estimates to produce a globally timed solution. So that's it. That's the sketch.
Could you say what, a little more precisely, what you mean by nonlinear stable, or by stable?
Right, so
What does that mean?
So if you were to go back to the original variables, you would see, you would initially take a small perturbation of your blob and it would wander off in some crazy direction if you measure it in t, but it would exist globally. However, there is a rescaling. There's a way to divide divide by a suitable power of t, both the density and the corresponding thing for the velocity, where you will see that these rescaled quantities for both solutions, both the background Sideris motion and the one that we have constructed, they are closed in precisely this topology. So that's the meaning of the stability. Otherwise, it's very hard to say what it means for a time-dependent solution to be stable. You have to agree on a certain way of comparing.
For gamma bigger than 503, you have linear and nonlinear instability. Is that correct?
I don't know.
Because of this term F1,
I-
that's like pumping instead
Yeah,
of
so
dissipation.
this is anti-damping. So yes, for this equation you can show that something is unstable, but whether that has any physical meaning is unclear. When you have a time-dependent solution and you use a rescaling, stable theorems will have a physical meaning. It could well be that if you prove instability here, it doesn't mean you've learned really much about the behavior of solutions. It could just mean that they follow a different scaling, and then you don't see it in this picture. Maybe it's offset by a log or something.
But if you can construct one unstable trajectory, it's enough to conclude on instability.
Yeah, in these variables, yeah. It has a meaning, but only in a suitable coordinate system. Yeah. Otherwise, I mean, in some. This stability statement can be translated in some invariant statement in the original variables. The instability statement cannot, a priori.
For seawater, gamma is almost equal to 1, is 1 plus a tiny bit. What can you say in this limiting case? Gamma goes to 1.
When gamma goes to 1, this fails. So the physical vacuum condition cannot be enforced. Because
Seawater is not vacuum.
No, but
Yeah.
the pressure is.
The pressure is rho to the power gamma. So if,
Yeah, but with respect to the constant, that is atmospheric pressure, it's not with respect to zero.
I mean, I have an honest answer. I mean, yeah, we can discuss.
Can you see this special value of gamma in physics?
5/3?
Yeah.
Oh yeah, I guess I forgot to comment. Almost all relevant values of gamma are between 1 and 5/3. So yeah, the diatomic gases. So 4/3 is something that people like to call the radiation case, although it's justified in the context of, say, general relativity. I don't know what it means here. 5/3 has to do with neutron stars. So if you were to equip this system with a gravitational interaction, then 5/3 would precisely correspond to what people refer to as a neutron star. So Euler-Poisson system would give you plenty of such. But the equations of state, I mean, it has to be said that these equations of state are still a cartoon, and I don't think even physicists agree on what is the correct equation of state for any given model. They make some approximations, and then they have some ideas. I mean, these theorems would still be stable even with respect, even if you altered rho to the gamma a little bit. So if you had a lower order correction, you could still prove something. But yeah.
Just a comment, if you don't have an adiabatic gas, then you'd need to take temperature into account.
Yes.
And your life would become suddenly much more unbearable.
Oh, I presume so. But you see,
Because almost everything you have there would depend upon temperature.
right. So yeah, you could argue this is in a way a mathematical convenience, but
Well, the adiabatic gas laws work very well within their range.
To be
You've got
quite
that
frank,
range. It's only when you move outside that range that they don't work. And when they don't work badly.
to be quite frank, one of my motivations for studying this was precisely to understand the role of what it means for things to be critical. There's a lot of jargon in the literature where people say something is critical in this context. Here you have a very precise way of doing it, and it may not be the only way, but at least it offers you language. And it allows to trace certain analogies to other dispersive problems. This result, even though it looks like there's some damping, it's all in rescale variable. This is really dispersion that's taking care of the global existence. So in nonlinear Schrödinger equation, for instance, you can trace analogy to what I just done. And that to me was sort of a marriage point between the adiabatic law and these interesting nonlinearities. But you're absolutely right.
Well, Maher, you said if you time at the end, you could do where you cheat. So this is perfect timing.
Many of them. But one point that I definitely left out is that is really important actually. All the cartoons I said are correct. One point very completely cheated is the fact that in this S variable, S time variable, the Sideris ODE is actually singular, even though it is the same ODE or it corresponds to the same ODE in the T variable, it blows up in finite time. So the correct set of variables, so this is telling you that these solutions are not self-similar. If it were not blowing up in S, it would be self-similar. This expansion is linear no matter how you rescale gamma and what the value of gamma is. So the correct set of variables would be what people in some fields of PDE like to call the type 1 change of variables, which is to pass to a certain logarithmic scale with respect to t. And then all these damping effects and things that I talked about would translate into presence of some favorable exponential powers of this new time variable. So that's what's really going on. There's a whole new layer of say work that you have to do together.
So, Sideris proved that ODE has global solution?
Yes, Sideris proved there's a conserved energy. So why? Well, it has to be a solution of Euler. So the ODE has to inherit some of the Hamiltonian flavor or whatever, the conserved energy. There's a Lyapunov functional that allows him to show. Yeah, and then you can really say a lot about the solution. As I said, they exist in incompressible contexts as well, and different phenomena occur.
Well, you allowed, in the theorem, you said you allowed 5/3.
Yes.
But in there, well, in your,
So
in your heuristics, you said that you need to strictly test the 5/3 the way you wrote
that's correct.
to get the dissipation.
So the reason for that is the fact that this S variable is singular. So once you pass to the logarithmic scale, time scale, which I mentioned briefly,
That gives you a little bit of dissipation.
that gives you just a little bit of dissipation to include the 5/3 case. And if this were a self-similar solution, you would not be able to include 5/3. So okay, so the deeper story is the following: from more sort of geometric point of view, 5/3 for Euler is precisely the case where you have the so-called quasi-conformal invariance, in analogy to the mass-critical nonlinear Schrödinger. So there's a change of variables, which is nonlinear, which takes one solution from one solution to another, precisely like you would have in the mass-critical nonlinear Schrödinger. So 5/3 is distinguished from that point of view. But when gamma is bigger than 5/3, I really don't know what's going on.
It's unusually when it works for 5/3.
True.
You expect these things to be open.
Yeah, absolutely. I mean, to me, even this pseudo-conformal invariance, this was a miracle. We thought we discovered it, but of course we didn't. So Denis Serre had sort of written a note on this in the 90s.
But in the nonlinear Schrödinger equation, this mass critical equation is unstable. There is a blob in a finite time.
Yeah.
So here it's the opposite situation.
That's
Borderline belongs to the stability region, while the nonlinear Schrödinger
that's
equation
why I leave
belongs to
loose
the
analogies for the Q&A session.